Welcome. This is Noson Yanofsky, Analysis of Algorithms. Today we're going to do a fun little chapter. It's called Chapter 16, Greedy Algorithms. Don't look at that for a second. Let me tell you what greedy algorithms. So let me just put it in context. Chapter 15 was dynamical programming. That's what's called a paradigm that shows up many different places. Greedy algorithms is another one. It's a lot simpler. The main point is finding where it works, because it doesn't always work. But when it works, it's a great little cute algorithm. Okay, so let's start with the first example. The first thing is called the activity selection problem. It goes as follows. You have a busy soccer mom, and she has to do this activity and that activity and that activity and this activity, okay? And she has a lot of tasks that she has to do. She has a lot of things that she has to do, and each task has a starting time and a finishing time. Okay, now what she wants to do is, but some of them overlap, so she won't be able to do them if they overlap. In other words, if she has to be here and pick up the kids, she can't be at work. So the activities overlap in time, and if the activities overlap in time, you have to choose one of them. Here's the problem. I want to choose some of the problems. I want to choose the maximal number of those problems. In other words, find me a way to find those problems, the maximal number of them. Okay? We're not interested in being busy the most time. That's not what our aim is. It's doing most of the problems. Now, it's clearly not, it's the beginning of a whole field. Okay? There's a whole field about this stuff in operations research and stuff like that. It's the beginning of the whole field, because here we don't care one job is equal to another job, but you can start putting weights on job and saying, oh, this job is more important than that job, and then you can want to do, higher weights. You want to accomplish jobs that are more important. Okay, but here we're just doing a basic example. All the jobs have equal weight, and we want to get the most jobs. Okay, so here's a typical input. The typical input is as follows. You have starting time and finishing time. These are the jobs you have to do. One starts at 3, the other finishes at 7. One starts at 12 and finishes at 14. One starts at 10 and finishes at 11, etc., etc. Okay? I just want to make sure that you could see the bottom of this. So somebody was complaining to me that, I think you can see the bottom just in case. Okay. Okay, so you can see the bottom of that. Okay. Question, how do you solve this problem? Okay, I'm going to give you the answer, and then we'll see another example, and then I'll explain to you why the answer works. Okay, but you can try to solve it yourself and see what should you do. Should you take 1 through 4? If you take 1 through 4, then you'll take 5 through 9. If you take 5 through 9, you can't take 5 through 8. So which one should you take, 5 through 9 or 5 through 8? Well, obviously here you should take 5 through 8. But maybe you shouldn't have taken 1 through 4. Maybe you should have taken 3 through 7. And you have to go through it. So try a few and come back and see which ones you have. How many you got? Okay. The book does another example. We didn't do the book's example. This is my book. Okay. Here's what you do. Here's the solution. What you do is you take your jobs and you sort them. You sort them not by how long the jobs are, or not by when they start, but you sort them by final time. Okay, so you sort them by F1, which is less than or equal to F2, which is less than or equal to F3, which is all the way to Fn. Okay, you sort them. By the way, sorting is n log n by this thing. Okay, and then you have your list of jobs, and then basically what you do is choose what you can. This is where the word greedy comes from. Greedy means, what does it mean, greedy? You grab what you can, don't worry about the future. The future will be okay. Okay? This is what greedy algorithms are all about. So let's go through it. You're going to grab 1 through 4. If you grab 1 through 4, you're not going to be able to do 3 through 7. Okay, great. You're also, you're going to grab 1 through 4, you're not going to be able to do 3 through 7, but you can do 5 through 8. So grab 5 through 8. 6 through 8 you can't do. 5 through 9 you can't do either, because you did 5 through 8. Okay? 7 through, so you are now busy till 8. So you're not going to be able to do this one either. But you can do this. So choose this. You are now busy till 11. Okay? But you won't be able to do 8 through 13. Whoops. Right? You won't be able to do 8 through 13. right? And you won't be able to do 12 through 14. Okay, so you got 3 jobs. Sorry, I made a mistake here somewhere. Yeah, no, you got 5 through 8. I'm sorry, you can do this. You got 4 jobs. Okay, you got 10 to 11, and you can't do this because you're busy till 11, and then you do that. Okay, so it works. Okay, you're not going to get better than 4 jobs with these things. Okay, you might get, well, anyways, you're not going to get better than 4 jobs. So it works. So let's just go through how we did it. You sort by final time, and then choose what you can. We're going to go through the algorithm in a second. No, we're not going to go through the algorithm in the book because it's too easy. But instead, I want to explain to you why it works. And the way to see why it works is to try another example. An example where I made up the numbers. So, I mean, I made up these numbers, but this one really brings it out to forefront. Okay? So, let's do that. Okay, so here's a nice example of a problem. I made up these numbers because I wanted to show you what it means. And we're going to see a pretty picture of describing these things in a second. Okay, you have starting and finishing times. Now, there are different ways people think of doing it. And I'd like to go through and show you why it doesn't work. You can take these things and sort by starting time. In fact, well, this is not sorted by starting time, but here, this is sorted by starting time. So just sort it by starting time, and then take what you can. Well, if you do that, you're going to take 1 through 15, and your last job is 15, so you're not going to be able to take this, you're not going to be able to take it, you're not going to be able to take any of them. Okay, so that was pretty stupid to take it by starting time. Now, a better guess is, look, I want the most jobs possible, so take the small jobs that don't overlap with any other jobs, and then you'll be able to have as much as possible. You get as many as you can. So let's see what happens when you do that. 4 through 6 is 2. This is a 2-hour job. This is a 2-hour job. This is a 3-hour job, 3-hour job, 3-hour job. Well, let's see what happens. If I take the 4 through 6, I could take the 10 through 12 also, but then I can't take the 2 through 4. Why can't I take the 2 through 4? 5. Hold on. Oh, I can't take the 2 because I get 4 through 6, so I can't take this, I can't take this, I can't take this, okay, because this overlaps with this. I can't take this because 10 through 12, that overlaps with that, and I definitely can't take the 1 through 15 because the 115 is the biggest job. If I take the 115, I can't take anything else because all my numbers are between 1 and 15. So again, if I take my starting time, I get 1. If I do by length, I get 2 jobs, but if I do as the algorithm tells you to, namely sort by final job, by final time, then look what happens. Okay, you're going to take 2 by 5, 2 to 5. That's a good idea. Okay, you are then not going to take 4 through 6, but you will take 5 through 8. Okay, because they're not. There's no overlap. When this finishes, this starts, so that's fine. Okay, you will take 8 through 11, okay, but if you take 8 through 11, you can't take 10 through 12, but you can take 11 to 14, so you got that, okay, and again, you can never take 1 through 15, because 1 through 15 is just everything, and so you can't get that, so you're not going to get that, but notice you get 4 jobs, 1 jobs, 2 jobs, 4 jobs, you like 4 jobs, okay, great, but I want to show you a nice way of looking at this problem. I mean, this is the book's way of looking at it. It's a very nice way of doing it, and so we're going to do it. This is 1 through 15. Okay, that's a giant job. Okay, but besides that, you have 4 through 6, and you have, I don't know, if I was normal, if I was 1, 2, 3, 4, no, that's already messed up. Okay, so let's not do that, sorry. Okay, 15 here, let's do 7, 8, whatever. This is way too much. 3, 4, 4 is here. So this is from 4 to 6. This is from 10 to 12. Okay, now 2 to 5, halfway of 4 to 6 is 2 to 5, so this is 2 to 5 is over here, and 5 to 8 is over here, and 8, sorry, I didn't do this exactly, 8 through 11 is over here, and 11 to 14 is over here. Okay, so maybe this should be, let's do this a little bit more evenly. This is 5 through 8, and this is 8 through 11. This is lined up. Okay, anyways, we're getting closer. When 8 finishes, 8 starts. Okay, great. Now, you could see what happens. If you take the first 1 through 15, you're not going to be able to take any of the others. The second idea was take the little ones. Okay? Take the little ones, take the little ones. Well, the little ones, you're right, they don't capture a lot of time, but in the sense they overlap. They overlap with these two. Okay? Again, I chose these numbers because I wanted to show this. Okay? But here's the idea of sorting by final time. What you do is you take, in some sense you could see it like this. Look, take the end of the first job first. Okay? So you're going to have grab what you can. Now the point is, if you're sorting by final jobs, the next job will not overlap that much. In other words, you've got that 5 taken care of, and that's the smallest 5. Okay? Then you take this guy, 8 is the next. Then you take this guy, 11 is the next. Then you take this guy. So again, you want to grab jobs that end early. That's what sorting by the final job is all about. You want to take jobs that end early. So that explains how it's done. By the way, the book does this, and the book does this on page 420, and you're reading it. So, question, how much work is done for this? Well, if you look at it, basically, what you do is, how much work is taken? Well, you take a list, you sort it. How do you sort it? What it doesn't matter what the algorithm is, but you then enter and log in. And then basically, you go through your list, seeing how much work is done, you go through the list, this list, not this list, not this, you go through this list, and you grab what you can, okay? And you're always looking, the end time is 5 here, so good, I can't take anything till 5 again. Oh, got it, 5 through 8. I can't take anything, the end time is 8, I can't take anything till 8. Got it. Okay, the end time is 11, I can't take anything till after 11. Got it. Okay, the end time is 14, I can't take anything till 15. Okay, it doesn't exist. Okay, so you got to do it. So basically, you went through the list like that, so that's plus n. Okay, and this is a member of O of n. O of n log n, sorry. Okay. Now, had I not known about this algorithm, this greedy algorithm, this grab what you can thing, I would have done this another way. How would have I done this? Well, look what I want. I want a subset of these jobs. I want the largest possible subset. So I would have gone through all possible subsets from the largest subset, seen if it works, and then would grab the largest one first. I would start from the largest subsets, all of them, till the smallest subset, just one of them, and I would have done it. That would have worked. However, to go through all possible subsets is 2 to the n. That's an exponential algorithm. Okay, that's an exponential algorithm. We don't want to do that. Okay, so greedy algorithm is a way of getting away from that. Great. I'd like to show you another problem where greedy algorithm does not work. Okay, and with this we'll understand what greedy is all about. Okay, so the other problem, you might have seen it already. You might have seen it already if you went through chapter 5 of my book, because it's called the traveling salesman problem. Okay, so let's just remember what the traveling salesman problem is. You've got to know got to have heard what the traveling salesman problem is. The traveling salesman problem is as follows. You have a bunch of cities. Okay? Let's say these are the cities. And the distances in between them. Okay? So you want to know the distance here? That's this. The distance here is that. I want to make this a little bit bigger. Let's do it again. Bunch of cities. You're not going to be able to take notes on this, but bunch of cities all over. I want to, let's just remember what the traveling salesman problem is all about. I think traveling salesman is all, I think we talked about this in class, by the way, but that's okay. You want to start at some city, visit every city exactly once. You're a traveling salesman. You want to go and visit every city exactly once, and you want to come back to the original city, and you want to do this in the shortest amount of distance. Okay. Now this turns out to be an NP complete problem. Okay. I'm sorry, and it's an n factorial problem, so it's particularly bad, and you'll read chapter 5 from my book and you'll see exactly how bad it is. Okay, but I don't want to do it that way. What I want to do is what's called an approximation algorithm. I want to do a greedy algorithm. I'm going to do a greedy algorithm, but I won't get the best solution. Okay? I want to do a greedy algorithm, but I won't get the best solution. The greedy algorithm is called the nearest neighbor heuristic. Okay, let's just go through it. What it says is start at a city. Pick any city, start there. Okay? Then go to the nearest neighbor. Go to the city that's closest to that city. Okay? Go to the city, and then once you're there, you visited 2 cities. Great. Then go to a 3rd city that you didn't visit already. Go to the nearest city that you did not visit. Okay? So basically, as you're going along, you look around all your cities that are near you, pick the city that you have not seen yet that's closest to you. That's a greedy algorithm. Okay? But let's see what can go wrong. Okay? So let's start. I need a piece of paper here. Don't move. Okay, don't move. Okay, let's start here. Let's see what happens. Okay, I want to go to the closest city nearby. What is the closest city? Now, you are looking at this from far away. I am looking at it from close. I think this is, right, I think this is closer, so we go here. That's my starting point. I go there. Great. Now, the nearest city from here is here. Okay, great. The nearest city from here is clearly here. Now, I just want to show you, I am grabbing the nearest city. It might be an idea, okay, so I'm greedily grabbing this city. It might be an idea to go far away over here and then deal with this and then come back to that later. Okay? And that probably is the right thing to do, but I'm following the nearest neighbor heuristic. I'm sorry, I didn't tell you what the word heuristic. Heuristic is like a rule of thumb, something that's kind of true. It's not always true, but it's kind of true. Okay, anyway, so we're following our nearest neighbor heuristic. We're grabbing the closest thing nearby. Okay, this is that. That's further, and that's way further. Okay, great. Okay. What's the nearest city from this that we haven't visited already? Clearly this. Okay, great. And I assume that is much better than that. Yeah, so we go here. And the nearest native for that is that. Okay. And the nearest city from this, here I have to walk away a little to see that. What is the nearest city? I guess up on top, right? So we're going to go like that. Okay, the nearest unvisited city is this. Nearest unvisited city is this. Nearest unvisited city, that's the only unvisited city. We have to do that. And then we have to go back to the beginning. Okay, so that is the way the nearest neighbor heuristic. Now, the point is, it works. It gives you a path, but it's clearly not the best path. Okay, let me show you why it's not the path. And I just want to point out, whenever you see this crossing, that means you're wasting space, you're wasting distances. Okay, so let's just do this. We started here, we went around like this, and went like this. So let me just show you a better way of doing it, and we'll see if it works. I want to clear up this crossing. So, you know what? Okay. Okay, so I'm going to clear, Okay, I'm going to clear up this crossing. So what I'm going to do is go here, and rather than go here, I'm going to go not to the nearest neighbor. That's the nearest neighbor. I'm going to go not to the nearest neighbor, and then go here, here, okay, and from the nearest neighbor of this is this, back to here. Okay, notice the green only has one crossing. The blue has two crossings. Okay, that's a waste. Okay, I'm going to fix this also in a second. I'm going to fix it with a different color. Let's do black. Okay, and it's going to go as follows. You ready? Yeah. Okay, it's going to go as follows. Just like before. But now, instead of doing this, which is nearer, I'm going to do this. Sorry about the sound effects. Okay, I did this. Okay, now notice there's no crossings. Now, that is not necessarily the shortest possible way of doing it, okay? But it's shorter than, so the black one is not necessarily the best way of doing it totally, but it's definitely shorter than the blue and the green, okay? Now, you cannot, okay, so what's my point? Why am I bringing I'm showing you the greedy algorithm is a nice algorithm, but it doesn't always give you, I'm sorry, in this case, it doesn't always give you the best possible answer. In the activity selection problem, it does give you the best answer, but in this case, it does not give you the best answer. Okay, so that takes care of that. Oh, one thing, I always get this question. Everyone says to me, why don't you solve the traveling salesman problem like this? Here's a solution to the traveling salesman problem. Do the nearest neighbor heuristic, and whenever you see a crossing, undo the crossing, like we just did. Okay, we got rid of the crossings. Okay, and then we'll have a clear, what's called a simple loop, without any crossings. Notice the black. Watch the black. Starts here, goes around, didn't cross any lines, goes here. Okay, so that's very nice. Anyways, that will not give you a good solution to the traveling salesman problem. Okay, this whole area is something we're going to see in section 4 of my book. They're called approximation algorithms. Okay, and what this is all about, this is a whole field, and it says as follows. NP-complete problems are very hard problems. Problems that are factorial and exponential are very hard problems. We can't solve them in a normal amount of time. Question, can we find polynomial algorithms that don't give the exact solution, but give an approximation to an exact solution? Or don't give the best solution, but give an approximation. Okay, and that's what approximation algorithms are all about. And this is an example of such a thing. Great. I'd like to show you another NP-complete problem. Okay. I'd like to show you another NP-complete problem that's also very hard, and then we're going to see if greedy algorithms can somehow help us. Okay. So these are hard problems, just like the activity selection problem seems to be a hard problem, but thankfully we had what's that thing called? The greedy algorithm to show us, no, it's not so hard and we can get the best solution. So I'd like to show you another hard problem, and it's called the knapsack problem. So let's do it. Okay. I'm going to call it what the book calls it at the end of the book. I'm sorry, at the end of, it's in Core Analysis and Revest, it's called the 0-1 knapsack problem. Okay, let me tell you what it's about. Okay, it's an NP-complete problem. I'll tell you, if you don't know what NP-complete is, that's okay, fine. You will by the end of the semester, I promise. It's a problem that's exponentially hard. Let me just tell you what it's all about. You're given a bunch of things. You're given n things, okay? And these n things, well, let me make a story out of it, okay? You break into a store with a knapsack, okay? You have a bunch of things that you can put into the knapsack to steal, okay? But your knapsack has a capacity, okay? And you can't fill your knapsack larger than the capacity. You cannot fill your knapsack larger than the capacity. Great. So what you want is to fill it, but you also, each thing that you put in, you have a certain, it has a certain price to it, okay, that you're stealing, and you want to make a certain amount of money doing that. So question, can you fill your knapsack below capacity, below or equal to capacity, and get enough goods to get your goal? Okay, good. So that's the story. Let's give it a formal definition. Okay, you're given S1, S2, S3, Sn. You're given n objects. Each one of them has a size. Also, each one has a price. P1, P2, P3, Pn. Okay. You're given two more numbers, so each one has a size and a price. You're given two more numbers. One is C, the capacity of the knapsack, and the other one is the goal, the financial goal, how much you want to get. And you have a question: yes or no? Can I fill some of these things into the knapsack below capacity or equal to capacity, and I should get more than the goal or more? So let's write it out. Okay. Question: does there exist a subset x1, x2, xm, a bunch of things, okay, subset of 1, 2, 3, n. Can I find a subset of these things such that the sum not happy with that. Sorry. Can I find, does there exist a subset, X subset of numbers? Is there a subset of numbers such that, so what is X equal to? It's equal to a bunch of numbers from 1 to n. Not all of them, maybe all of them, but not really all of them. So does there exist a subset such that I equals 1? No, let's not write it like that. Hold on, sorry. I member of X. Those things in I. Si. If I add up all those things in this subset, I get less than or equal to capacity. Okay. Furthermore, so let's write, and the sum of all the things in X, if you add up their prices, you get more than or equal to the goal, the financial goal. Okay? And that's a question mark. Does there exist a subset such that when you add up all the things in the subset, you're within capacity, and when you add up the prices of all the things in the subset, you get G. You get the goal or higher. Okay. Now, I don't know how to solve this problem, except to try all possibilities. Try all possible subsets. Brute force search on all 2 to the n possible subsets. Great. There's a problem with that. 2 to the n will take trillions of years. If I have 100 elements, it'll take trillions of years. Okay, great. Now, but you have a solution to this. I hate to be rude about this. Okay, we can erase this. This makes sense. Okay, but you have a solution to this. You know what to do. You have an algorithm in your head of what to do. Let me just explain to you. Let's say you break into Kings Highway Mall. Okay, it's 12 o'clock. They close at 11. You break into the mall. Which store are you going to go to first? What was that? Ah, yes, the jewelry store. Why? Why jewelry more than the car store? There's a car store there. Okay, and the answer is, I mean, cars cost $20,000. Okay, and the answer is you're going to go to the jewelry store because you can fit the jewelry into your backpack. Okay, and so you're going to do that. So I'd like to do the following. Okay, I want to formalize that. Why jewelry? Well, the answer is for the prices that you get and the sizes that you get. It's the best thing to do is go to the jewelry store. Okay, you don't want to go to the toy store. You don't want to go to the electronics store. You want to go to the electronics store. You can't do. I mean, this camera that I'm looking at is a good $300, and it's very little. So the electronics store is probably a second choice, but you want to go to the following. So I don't know a name for this. I go as follows: take the profit. The ith profit divided by the ith size, okay, I call it, okay, the preciousness, okay, because I watched Lord of the Rings too much. Precious. The preciousness, the ith preciousness, okay, but somebody, a former student, said it's called the profit density. Okay, I don't know. The ith profit density. So here's what you do. You ready? And obviously, look at that. Jewelry, small things, large profit. Okay, they can fit. A lot of them can fit in your. Knapsack. So you want to go through that. So here's a greedy algorithm. Ready? Here's a greedy algorithm. Greedy algorithm is as follows. Take your profits, take your sizes, calculate for each one of them the profit density, the preciousness of each one. Sort them by that, okay? And then grab what you can of that. Now, if you think about it, obviously you're going to spend the most time in the jewelry store, okay? But we'll deal with that, okay? Great. So it seems, okay, but again, boats, it says here, cars and boats are not precious. They're big, so they don't have a good preciousness. Okay, their size is very big, so even though their profits are big, but they don't have a lot of preciousness. Great. I just want to tell you why this doesn't solve the traveling salesman. I'm sorry, the knapsack problem. Okay, this will give you an approximation to the knapsack problem. It's an approximation algorithm for the knapsack problem that doesn't give you the best possible solution. So let me just show you let me just show you an example. I made up this example to show you where it doesn't work. Okay, so it goes as follows. Okay, you have P1. I'm sorry, S1. I'm sorry, I want to do P1 on top of S1, so we can talk about P1 is equal to 99. I make $99 if I get that. Okay. P2, sorry. P2 is $100. Okay, great. S1 is 1. S2 is 100. Okay, great. The capacity is 100. And instead of giving you the goal, I want to find the most money I can make. So let's go through it. The preciousness of this, one is P1 divided by S1, which is 99. The preciousness 2 of this is 100 divided by 100 is 1. Okay, so what are you going to take? You're going to take the more precious thing first. Okay, so look what you're going to do now. Okay, you're going to take in your knapsack, here's your knapsack, you're going to take one object, which is of size 1. You can take this object of size 1, okay, and its worth is $99. Okay, now you say, oh, the capacity is 100, let's take this. No, because if you push this in, your capacity will be, you'll be over capacity, you'll have 101, not kosher. Okay, so you have to choose, if you're following the what's that called? The greedy algorithm. Okay, you'll have to choose this. You'll make $99, but you won't do that. Okay, great. But if you don't follow that algorithm, look what you'll do. You'll take 100 of these. You'll make $100, which is better than $99. Here you make $99. Here you make $100. Okay, $100. You didn't take that, and you're very well. Okay, so question: which one should you do? So it's very interesting. Should you take something that's worth $99, or should you take 100 things that are worth $1 each? Okay, and the answer is you should take that. Okay, so that's called what? Let me just go through what I just showed you. We had the ZeroOne knapsack problem. I told you it's an NP complete problem. We tried a greedy algorithm by sorting by preciousness. We saw it doesn't, usually it'll give the right answer, but it doesn't always give the right answer. Okay? I'd like to talk about another problem called the fractional knapsack problem. The fractional knapsack problem, which is like the ZeroOne knapsack problem, except it has the following property. Okay? Okay? Again, the fractional knapsack problem, you're given a bunch of sizes, you're given a bunch of prices, you're given a capacity, you're given a goal, okay? But you have the following. You're allowed to take part of things. Okay? The problem here was I couldn't take part of these things. Okay? You either take something or you don't take it. ZeroOne knapsack problem. You either take it or you don't take it. But you can't take fractions. You can't take part of it. The fractional knapsack problem, you can take parts of it. Okay? In the fractional knapsack problem, you can take parts of it. Okay? And that's what this is all about. This is called the fractional knapsack problem. You're allowed to take parts of it. Great. Now, this is not an NP complete problem. Let me tell you why. Because I have a great greedy algorithm to solve this. What? I do it with preciousness. So let's just solve this problem with the greedy preciousness algorithm. I take one of these. Okay, it's worth $99. That's great. I like that. Then I don't take all 100 because all 100 won't exist, but I take 99 out of 100. Okay, and I'm not going to get all $100 because I didn't take all of them, but I get plus 99 again. I get 99 other dollars, and if I add that together, I get 198. So the fractional knapsack problem is an easier problem because I'm allowed to break up what I'm taking and doing it. the way to think of the fractional knapsack problem is instead of breaking into a mall and going which store to go to, let's say you break into a store that sells spices. Okay, they don't have good spices stores here, but if you ever go to India, they have these great spice stores. The smell is amazing. Okay, you go to India and you anyway. So if you break into a thing like that, you have a knapsack. When I went to India, all my relatives called me up. Oh, you have to get me this. You have to get me that. Whatever. Anyways, there are some very expensive spices that they sell in India. And if you were to break in, you'd go to the most precious one. Okay, fill your knapsack with all of the precious one that they have. I forgot the name of the precious one that everyone wanted. Okay, and then try this and then try that and go through it from most precious to less precious until your knapsack is full, and then you go. Okay, so that takes care of that. Okay, I'd like to do section 3, and we'll start in a second. Okay, so this is called the Huffman Codes. Huffman Codes is an example of a greedy algorithm. And what it's there is to compress things. So all compression algorithms use, many compression algorithms use this. So if you have a picture and it's very, very whatever, and you want to compress it to a smaller thing, you use something like this. Okay? I don't want to get into that stuff, lossy compression versus lossless compression. We don't want to get into this, but the idea is very simple, and it's a greedy algorithm, and also it's going to have some things that we talked about many times before, namely how we like our trees. We love our trees, and we love talking about trees. So that's what it's all about. So imagine the following. Imagine you're given a file, and the file has a bunch of letters on it. But the letters are only 1, 2, 3, 4, 5, 6. They have 6 different letters in it. Okay? And you know beforehand how often these letters show up. If you don't know it, you can go through it and you can count how many letters these show up. And they follow the typical rules of English language. So A shows up very much. A is a vowel. It shows up 20,000 times. You're given this file, it shows up 20,000 times. O shows up 28,000 times. It shows up even more than A. Q is rare. It only shows up 4,000 times. U shows up 17,000 times. Y shows up 12,000 times. And Z shows up 7,000 times. Okay? Now, what you usually do is as follows. You encode these 6 letters with some bits. And we do this with ASCII. This is what all ASCII is all about. You encode each one of these letters with a bunch of bits, okay? And the bits you can then decompose and read the bits, okay? And find out what it is. Okay, so this is a typical thing you do. You might do something like this. You say as follows. Again, the purpose is to decompose it. So you might say, when I read 000, I want to think of A. When I read 001, I want to think of O. When I read 010, I want to do Q. So we can even write this down. Okay, U is going to be 011. So we're going to write that down as 7. This has 17,000. Y is going to be 100, and Z is going to be, which is 12, and Z is going to be 7. Okay, and again, you can make each one of these a 3-letter code. So let's just do this. This is 000, and then this is 001, and Q is 010, 010, and U is 011. Let's just finish it for the hell of it. 100 and 101. Okay? Sounds like a very good idea. Okay? Question. How many thousands of bits do you have? Let's do this. 20 plus 28 plus da-da-da-da. How many letters do you have? 20 plus 28 plus 4 plus 17 plus da-da-da. I counted them out, and it's 88,000 letters. So you have 88,000 letters. Each letter is going to be represented by 3 bits times 3, so this is letters, times 3 bits, okay, equals how many bits will your file use? And the answer is 264,000. Okay, so that works out very nice. Okay, but there's something stupid here. There's something very stupid here, and that's as follows, and we're going to fix it. So the question is, can I store it, this file, with less than that amount of bits? And the answer is yes, you can. Okay, here's the stupid thing. The stupid thing is as follows. Notice, to get to A and to O, you have to go through 3 letters. Wouldn't it be better if you had 2 bits for these, because they show up very often? Okay? And wouldn't it be better, we're putting all these things at the same level as this, but these show up much often. It would be you would save a lot more if you did it. And that's exactly what Huffman Codes does. It uses a greedy algorithm to come up with a better code. Let me show you how it works. Okay? It's a lot of work, but it's not hard, and it's not hard, and it's not good. Okay, so here's what you do. You have, I'm sorry, I should have put this. You have 4, 7, 12. I am sorting in increasing order the popularity of those letters. So we have 4, 7, 12, 17, 20, 28. Okay, from lowest to highest. Okay, I know what these letters stand for. I'm going to put that in later. But what I'm going to do is build a tree like I just had over here, but I'm going to build it using this concept. The concept of, you know what? I want the less popular things to be at the bottom of my tree. Okay? I want the more popular things to be on the top of my tree. Okay, if I want the less popular things to be at the bottom of my tree, I better choose them first in building my tree, because I'm going to build this tree, and you're going to see the way I build a tree. Okay, so I do as follows. You take they're in the increasing order, choose the 2 smallest ones, and put them together. Choose the 2 smallest ones. So these 2 are the smallest ones, so I'm going to have 4 and 7, and I'm going to have 11 over there. Okay. Now, you take out 2 and you put it back in there. We'll talk later about how to do this algorithm, because we're actually going to go through this. But now you also have a 12, you have a 17, you have a 20, and you have a 28, just like before. Okay, great. Now, just notice these 2 guys are already, they're not a root of your tree. They're lower from your tree. Okay? Next thing is as follows. Choose 11 and 12. 11 and 12 are the 2 smallest things on your tree, so we're going to choose them. Let's do it. 11, 12. 11 is equal to 4 and 7. 11 and 12 is 23. 23. Okay. Now 17, 20, and 28. Okay, great. Okay, so that's your new tree. We're basically putting things on your tree, combining them. Okay, next, choose the 2 smallest things from your list. The 2 smallest, you're going to use a priority queue. You'll see in a second. You can use a priority queue. Okay, so let's do that. We're going to have, let's do it over here. Let's do it over here. You're going to have the same 23 over here. I don't want to recopy it. You have to recopy it because you have more papers, but I don't know how to recopy it. I want to do this together, and this is going to give you 37. I'm going to put that back in. Okay? Great. Okay, so now I have 3 things. This, this, and this. What's the 2 smallest ones? For the hell of it, I always have like this. Okay, the 2 smallest ones is 23 and 28. So let's redo this. So it's going to be as follows. We'll do it right over here. Ready? 23 28. What's 23 plus 28? This is why I hate teaching without students behind me. 23 and 28 is 51, I believe. Let's check it out. Yep, 51. Let's just fill in that point. So I have 23 and 28, and then I have what's left. Okay, so what's left is 23 and 28. I'm sorry, 23 and 28, and what's left is 37. Okay. Let's just fill in the 23. The 23 is 11 and 12 and 4 and 7. Okay, and now I'm going to bring those together and make my final thing. So this is going to be my final tree. The final tree is going to be 88 because there are 88,000 letters in my thing. So notice what I'm doing. When I'm bringing a tree together, I'm adding up the things. So if I'm going to have one root node, that means I'm going to have 88 things all together. So I'm going to have 88, okay? He's going to have two children. 51, we're going to have the smaller children as always on the right. So this is 51 and 37, that's 88, okay? Oh, where's I'm sorry, I left this out. 37 is 17 and 20. Okay, 37 is 17 and 20. That's very good. Okay, now what the hell is 51? 51 is 23 and 28. What's 23? Here's 20. Oh, here's 20. Okay, where's 20? 23, okay, great. 23 is 11 and 12, and 11 is 4 and 7. Okay, so that is very nice. Just notice what's happening here. The larger numbers, like the larger leaves, like 20 and 28, are high up. The smaller leaves are on the bottom because we chose them first, and we always chose them and they went to the bottom. These 28 and 20 and 28 were chosen late. So that brings it together. Okay, great. Now we're going to add in letters to this. I'm sorry, bits. 0, 1, 0, 1, 0, 1. The left is 0, the right is 1. Okay, and now we're also going to add in what these things correspond to. 4 corresponds to Q, and 7 corresponds to Z. Those are the unpopular letters. As opposed to that, 20 is an A, and 28 is an O, and 17 is U. We have to color we have to give to all the leaves. Okay, and now we're going to make, so let's just show you the greedy algorithm before I erase this. Let's just remember what we did. What we did was we sorted them into increasing order of popularity. Okay, we grabbed 2 of the smallest, put them together, and put them back into the tree. And we grabbed 2, put them back, put them together, then put them back. Grab 2, put them together until you only have one thing left. Okay, great. So now let's make a code for this. Okay, let's do it. Q is 0, 0, 0, 0, and Z is 0, 0, 0, 1, and Y is 0, 0, 1, and O is 0, 1, and U is 1, 0, and A is 1, 1. Again, The U and the A show up the most often, and they only have 2 letters, 2 bits to get them. Okay, let's do a little calculation here. This has 4 bits. I'm sorry. Let's go through. Let's do that another way. That's not right. We wrote the how popular they are in the beginning. So Q was Q had 4,000, Z had 7,000, Y has 12,000, O has 28,000, U has 17,000, A has 20,000. Okay, and how many characters does this have? This has 4 characters, 4 characters, 3 characters, 2 characters, 2 characters, 2 characters. Okay, so if we were to use this code rather than the code before, we would have 16 bits, 16,000 bits representing Q's. We'd have 28,000 bits representing Z. We'd have 36,000 representing Y. We'd have 56,000 representing this. All these are thousands. Okay. We'd have 34,000 representing U, and we'd have 40,000 representing K. So, question, how big would our file, how big would it be? And the answer is 210,000 bits. So we took the single file, okay, we stored it, but rather than storing it a typical way, assigning to each one 3 characters, we did the Huffman code algorithm, and we had some better, some worse, some 4 bits, some 3 bits, some 2 bits, and we got from 264,000 bits to 210. That's called compression. That's a nice compression. Okay? I just want to show you, you might say to yourself, hey, this is stupid. Why is it stupid? Because you might say, look, it's very easy to decompress the 3-bit things. You know, every 3 bits is another letter. Okay? Every 3 bits is another letter. Here, sometimes it's 4, sometimes it's 3, sometimes it's 2. How do you decompress this thing? How do you decipher it to do it? Anyways, it works better here, and I'll tell you why. Because if you looked over there in our first example of what the code, sometimes you'd have a sequence and there would be no letters. Remember, for 3 each, you can have 8 different symbols. But here, okay, but we only used 6 of the symbols. So you could have had unused symbols. But watch this. I'm going to randomly do this without looking at a paper. 1 0 1 1 0 1 1 0 0 0 0 0 0 1 0 0 1 0 0 0 0. Okay? Question. What the hell does this correspond to? Answer. I don't know. Let's try and look it up. Okay? So what I'm going to do is I'm going to keep this hand over here and I'm going to go through here. So 0, 1, that's an O. 0, 1, that's an O. 1, 1, that's an A. Okay. 0, 1, we know is an O. 1, 0, no, I'm sorry, what's 1, 0? 1, 0 is a U. Okay. 1, 0 is again a U. 0, 0, 0, 1. That's a Z. 0, 0, 1 is a Y, and 0, 0, 0 is a Q. Okay? So any sequence is easily decomposed like that. Okay? Just climb down the tree as you're reading it, and it's very nice. Great. I want to go through the algorithm, and I don't want to waste your time. Okay? So here's the algorithm. It's on page 431 of the book. And it goes as follows. It's an easy algorithm, we already understand it, so, but we'll go through it. Huffman, the input is a set of characters, but the set of characters has built in it the frequency. Okay, each character has a frequency with it. Okay, so they set n to equal to the number of elements, and then you have as follows. Q is equal to C. Q put into a queue. What's Q? It's a minimum priority queue. We saw this in chapter 6 when we talked about priority queues. We talked mostly about it in the heap sort, and I said then it's used all over. Well, here's one place it's used over. However, in heap sort we talked about a max heap. Okay, where the largest thing is on maybe right. I'm sorry. Right. The largest thing is the max. The thing on the top is the largest. Okay. But here we're going to talk about a min heap. Okay. The largest thing with the thing on the top is the minimum. Okay. So you have to invert the rules to get it. Great. Here's what you do. Notice what you do is let's just before we look at it, let's just remember we grab two things, we put them together, and we put them back into the heap. So we took out two things, we put one back in. So if we want to get through all of them, we have to do through n minus 1. Okay, and we'll actually pull out the nth one later. So here's what you do. You do it for n minus 1 times. First, get a new node. Allocate a new node. Okay, then we'll call it z. Great. Then z dot left is equal to x. That's going to be the first thing. And extract min q. Pull out one of them. Okay, and this is what I said. The smallest is going to be on the left. Always. The algorithm on the smallest one pulls out the left. Okay. Next, z dot right, okay, is equal to y, which is equal to extract min again. So you go and again pull out the second smallest one. So this was the smallest one, you pull out the second smallest one. Okay, you have two nodes, we call them x and y. Okay, and then the frequency, I told you every single character has a certain frequency. The frequency is equal to x dot frequency plus y dot frequency. So that's very nice. So you pull it out, and then what do? You take that thing that you pulled out, you put it back into it. So insert into the queue. That's a min priority queue. Insert the new node z with these extra things attached to it. Okay, great. You do that n minus 1 times. So you're going to start off with, let's say, 15 times, 15 characters. You're going to pull out 2 of them. You're going to have 13. Put them together in a new node. Put it back into the min queue. So you're going to have 14. Then you're going to have 14. You pull out 2 of them. You're going to have 12. Put them together. Put them back. You're going to have 13. Okay, 13. Pull out 2. 11. Put one back in, 12. Okay, you're going to go down until you're going to have one thing left. Return, extract, min, q. And then you can build your code based on that. So that's the Huffman code. It's a beautiful little code, and it helps you very much. And again, all compression algorithms work with this basic idea, and it's an idea that we saw before when we talked about optimal binary trees, where you have the more popular things on top, the less popular things on the bottom. It works all over. Okay, so I told you in the beginning when we talked about trees, we're going to spend every day of our lives talking about trees. We like short trees, but we like popular things on the top of the short trees, etc., etc. Okay, next, so we are now finished our paradigms. Chapter 17, I don't want to talk about. The rest of the chapters, a lot of the next few classes are going to be graph algorithms. Okay, have a great day.